one normal to the ellipsoid. If I consider a plane passing through this normal, and by that plane I cut the surface of the ellipsoid, I get this intersection. Now consider another plane which contains this normal ellipsoid with the rotation. Then I continue it to the ellipsoid and cut the ellipsoid again. And you consider another plane which goes through this line and cut the ellipsoid. As you see, we can have infinite number of planes which can contain this normal to the ellipsoid. And the normal section is in fact the intersection of this normal plane to and the ellipsoid. Normal plane is a plane can have the normal to the ellipsoid. We can have infinite number of them. Amongst all the normal sections, one of them is perpendicular to the local meridian. This section, which is in fact a circle, has a radius, which we show it by n. There is a mathematical proof for this formula, but if you are interested to see it, you can look at the reference that I have introduced in the caption or at the end of the lecture. Radius of this sphere is called radius of prime vertical, and you can compute it simply by this formula. A, semi-major axis of the ellipsoid, E2 is the first eccentricity, and phi is the geodetic latitude. Meridian radius of curvature. Consider a figure, and you have the normal to the ellipsoid. Here you have the geodetic latitude and 2 points at the surface close to point P. Consider from with the same distance from both sides, towards north and towards south. We already know that from the three points which are not along a line, we can have a circle passing through them. So we have a circle here. Now consider that these 2 points are now closer to point P. And we have another circle which has a smaller radius. And now consider even closer. Then we have another circle. When these 2 points get very, very, very close to point P, then this sphere, which is defined based on these 3 points, is called osculating circle. This osculating circle has a radius. Radius of this osculating circle is here. There is a mathematical proof behind it, but if you are interested to that, look at the lecture note or look at the references. But simply you can compute this meridian radius of curvature by having semi-major axis of the ellipsoid, first eccentricity, and geodetic latitude. Now it's time to see an example of how these two radius of prime vertical and meridian radius of curvature are computed. Consider the WGS 84 reference ellipsoid with these parameters and a geodetic latitude of 55 degrees, 25 minutes, 30 seconds. So the formula for the prime vertical, radius of prime vertical, is here. Just simply insert the numbers in the formula. You will get this value. And for the meridian radius of curvature, you can do the same. Just insert the numbers in the formula and you compute it. You see that they are around the radius of the Earth. So we have seen that the radius of curvature is changing from one point to another at the surface of the ellipsoid. But the question is that how can we find one radius for points or all over the globe? So as we see here, we have global radius and local mean radius. The global is simple because it is not a function of any points. It doesn't depend on any latitude. It's global. So we know that two axes of the ellipsoid are equal. So A and A. And the third one is B. We can take the average. It's the simplest form. Or we can multiply all of them and take the cube root. These are the global values for the radius. Local, the first one, local mean radius. We have two of them. We can define a Gaussian radius for 1 point. M is the radius of curvature along meridian at a point, and N is radius of prime vertical. We multiply them and take the square root of them. This is called Gaussian radius. And we can have Eulerian radius based on this formula. Eulerian radius is defined between 2 points. But Gaussian radius is defined only at 1 point. It should be clear. But Eulerian radius at 2 points. And this alpha is the geodetic azimuth between the points. Discuss later. Mi and Ni, since I is defined as the first point, therefore this is radius of curvature, the first point, the radius of prime vertical at the first point in the formula. Now let us see another example. So consider the same ellipsoid and phi, the same value that we have used for the previous examples. So A, we have already computed B in one of the examples. So we take the average, we come to that. If I multiply them and take the cube root, I will come to that value. For 1 point, at this point, we have already computed the radius of curvature along meridian and also radius of prime vertical. If I multiply them and take the square root, I get the mean radius at that point. And Eulerian, I have already defined here geodetic azimuth. Therefore, it's just simply I set M, N, and geodetic azimuth to get this value. Again, consider that azimuth is defined between 2 points. So Eulerian radius is defined between 2 points.